0, where are we? If t is 0, where are we? We're at 0, right? This is linear, right? This is still linear. And the idea is that this helical staircase, if you were to unwrap it, right? If you were to unwrap this thing, it would be like a ramp, wouldn't it? It's just that you're walking along the ramp and going around. So it is a linear increase in your z. So this is linear. At 0, you're at 0, so you're on the ground. And at 6 pi, if you plug 6 pi in here, 6 pi over 2 pi gives you 3. And 3 times 30 gives you 90. Right? Another way you could have seen this maybe is to write it like this. 90 is where you want to start, right? I mean stop. And then you could say t over 6 pi like this, so that at t being 0, you get 0, right? But at 6 pi, you get 1. 1 times 90 would give you 90. So it's like this is the height you want to wind up at, and this is like the slope, if that makes sense. And then now if you reduce that, you get this. Okay? Does that work? And then we could even clean that up. That's just 15 over pi t. All right. So I'm not sure why you said 30 over 2 pi. It works. Were you just trying to make it work in your head?
I divided 90 times 3 because there's 3 circles.
Okay.
3 times just divided by 2 pi because that was
Yeah.
circle and times 3.
And it works, right? Okay, so whatever in your mind works. So this right here, 30 over 2 pi t will work. I'm going to reduce the fraction 15 over pi t. We good? All right, moving on. You ready? You guess? Okay. We needed the path r of t. We needed the path r of t. We need the field. So what do you think? From reading the problem, what do you think our field is going to be? Which one? And put it in where? This? This is like an hour and a half ago. It was like an hour and a half ago. Yeah. Right. No, this is the, what is this? What is this the formula for? It's the area of the curtain, right? Yeah, so this is your surface evaluated along a curve. This is with respect to arc length, A to B. So, okay. Give you one, no? No? Okay.
Is the field gravity?
Field's the only force in play here, which is gravity.
Yeah.
That's the only force out here,
Yeah.
is gravity.
Yeah. Gravity.
Yes?
Maybe that one we had at the beginning of class where it was like x over the distance formula, y over the distance formula, z over the distance formula for each component. Is it some...
Oh, okay, excellent, okay. So now, so what's being suggested is that field from the very beginning of class where I said that this vector field is what we use for gravity where it's center seeking, right?
Oh, yeah.
Okay, now we all know, we have probably, how many of you have not taken a physics class? Never taken physics? Okay, so everyone here has taken a physics class. We should all know that when it comes to, physics, you can, it depends on how precise you want to be. So like if you want to know if you drop an object, how long it's going to take for it to hit the ground, you can use a parabola, a quadratic function to find that if you neglect air, right? If you want to throw air into the equation, then you have to factor it in, and then your function becomes more complicated, right? This is the same thing here. Do we want to look at gravity as being straight down? Because technically it's not. Because the center of the Earth is not the center of a sphere because the Earth is not a sphere. It's not perfectly spherical, right? So the question is, how anal do we really want to be here? Do we want to use the vector field that is center seeking? Or do we just want to say, hey, look, we're going to look at his gravity as being straight down? I think that's what we should do. Straight down, we'll get close enough. Yes?
With the other one, you have to figure out the radius of the Earth.
We would have to know where we were on the Earth. Because now the position of the silo would matter. You have this non-uniform, I'm exaggerating, this non-uniform Earth, right? And if your silo's over here, right, but your center of mass is here, right, then the center-seeking vector like that is not necessarily straight down anymore. So there's a lot more. Now, this is where it gets into like how precise do we need to be, right? And that's what makes things get more complicated, right? If you drop an object, that's one thing. If it's spinning, that's another thing. If it's got, you know, if it's a ball spinning, like a bowling ball spinning, versus a ball wrapped with sandpaper spinning.
Rolling without slipping.
Yeah, I mean, there's, right? And that's what makes physics become more complicated. We try and do a mathematical model the best we can, and the more accurate you want to get, the more things have to be factored in, right? So we are going to, this is like the no error problem here. We're going to say gravity is straight down and it's good enough for what we're doing here, all right? All right, so what is it? What's the force? I still don't know what the force is. I know you've said gravity, but what is it? Straight down. It's a vector straight down. It's 0, 0, and it's straight down, so it's going to be negative. And is it constant? Yeah. It's what though? I mean, what is it?
32 feet per second.
That's acceleration of, you're talking about something else.
Yeah, the mass. So it's mass times acceleration.
Okay, mass times acceleration,
Yeah,
which is weight.
yeah.
Does that have to do with his weight?
It's his weight. That's all it is. It's his weight. That's all it is. Okay? It's his weight. That's the force that's opposing his movement up the whole time, right? Gravity is against his weight. So this is a force of negative 200, right? It's 200 because he's carrying a 20-pound tool bag. That's it. It's a straight down vector.
Way overthinking.
Yeah, yeah. Okay, we good?
That would have been.
Now, let's set up the integral. We want the integral over c of f dot dr. That's what we want, right? That's going to give us our work. But do you see why in physics they tell you not to give a shit about what's going on left and right? They only tell you to worry about what's going on up and down? Why? Because if you're saying gravity is straight down, your dot product of these two things are always going to kill off the first two. And all that ever is going to matter is that last component, which is your vertical displacement component. Right?
Yeah.
So I said in the very beginning, you could solve this very easily in physics. But we're trying to get this from a perspective kind of further out, okay? So now let's set this up. This is going to be the integral from 0 to 6 pi. And then we have 0, 0, negative 200. Dotted with who cares, comma, who cares, comma, 15 over pi t dt. When we dot all that together, we get integral 0 to 6 pi, and then this times that, right? What's that? Negative 3,000 over pi dt. And now that's just a simple integral, right? Negative 1,500 over pi t squared. Was I wrong to say that's simple?
I don't know.
I mean, that a constant times t, the antiderivative is constant 1/2 t squared,
Yeah.
half of 3,000.
It's a big number, but
Yeah.
I just.
So this goes here, right? 6 goes here, the pi's cancel. 6 times 1,500. What is that? 6 times 1,500? What is it?
6 squared actually, yeah, t goes 6 pi goes into the t squared.
Oh, I forgot to square. I'm sorry. Yes, I'm sorry. I forgot to square it. I just put it in as t. My fault. So we get negative 1,500 over pi times, and then you plug in that, so you get 36 pi squared. And then when you plug in 0, it's all gone. So this is going to give you, one of the pi's cancels, so 36 times 1,500. And then times, someone do that. 1,500 times 36 times pi, do like an approximation, 3.14. And let's see what we get.
I can see this. Because I'm the future.
It's going to be a big number, but
169,646.003.
foot-pounds. It's negative
Yes.
because you were going in the opposite direction of the force, right? The force was down, you went up, it's negative work. All right.
Hey, we actually got a number of
So those of you who are physics people, because I haven't taken a physics class in a long, long time, how would you have done this problem? Does anyone know how they would have done it? Like, quick.
Man's weight to mass, so that way you can do the mass and then times that by and plug it in for
Like, would you have come up with this part right here? Like something like this?
some of this sort of
No? What would it have been? Yeah? Oh, the distance. Wait, 180? Wait, 200 times 90?
because the force displaced is the person carrying that carrying up against gravity, so you multiply whatever that the man's mass is by negative 9.8, and you put it in reverse, which gives you your normal force.
Wait, negative, well, 200 times 90 is not the same answer, right?
Oh, no, you multiply by gravity.
Oh, okay, yeah, okay. So again, I'm not, I don't look at it from the physics perspective. See, the way I look at the physics perspective is it's one unique scenario where your field, your field, vector field, is a constant, right? A couple of constants, pointed straight down. That's like a very simple vector field. I look at it more, I guess, mathematically, like this could be anything. Like, look at the next example. Oh, you know what? How about this? I'll offer this as a bonus because I know a lot of you are like really wanting bonus. 10-point bonus on one of your mini exams. That's a pretty big bonus. And it's not like a super hard problem. It's just a slight tweak to this problem. So, so let's take the same guy, right? And he's walking up this same silo, all right? And he's carrying a 20-pound pail of paint instead of a tool bag, all right?
Oh,
Okay? But the paint has the thing has a leak in it, all right? So what's happening is that as he goes up the silo, right, he starts out with his 20 pounds of paint, and by the time he gets to the top, there's only 16 pounds left. Okay? So the question is, how much work was done? Do it this way with what we're doing in class. Don't go use some physics formula for it, okay? I want you to just do it this way. And that'll be to be turned in next class. And while I'm thinking of that, so I've made decision on the mini exams. The way we're going to do the mini exams is I'm going to let you do 6 total. I'll grade your best 4, all right? So those of you who feel like you want to get another hack at a better grade, I think I said you could do 1 more, but I'm going to say you can turn in 6, all right? Yes? If you're happy with the 4 you have, be happy. If you've only done 2, then I would get on it pretty quick. If you've done 3, you know that you can do 3 more. Okay, it's up to you. Everyone understand this problem? The slight change. Okay, that would be due at the beginning of class next time. We have one more problem, then we're going to go. Take a look at this one. Everyone have a chance to look at it? So we're trying to calculate the work done on the object during this time period. So t is 0 to 1, so t is like time. Maybe that's 1 minute, maybe that's 1 hour, maybe that's 1 second, who knows what that is. Right? So when it comes to these problems, we need two things, right? Really? We need the path c written as a vector function, r of t, and we need the field. What do we have? We have the path. It's there. It's been handed to us on a silver platter. There's the path. We even have the restrictions on t, right? So the only thing really left for us to resolve is the field. So I'm just curious what you think of this. How is this problem different than the last one? It's metric, 10 kilogram object, right? It's kilograms, pounds, they're the same, just no? Are they the same?
No, they're not.
No. What's the big difference between kilograms and pounds? Kilograms is what? Is a mass. And pounds is a weight. And they're not the same thing. And in the previous problem, the man was walking around the silo. We assumed he was on Earth. Right?
Yeah.
Okay, here, this object is moving in this path, and there's no mention of anything. You're not on Earth or anything. It's just, this is an object moving through space. So there is no mention of gravity here at all. Right? So you cannot assume there is gravity. Okay? So how are we going to come up with this field? Remember, work is equal to F dot D, right? D is the displacement vector, and F is the force, right? The force, right? This is the force. How are we going to get our force if all we have is the mass? I'll give you a hint? No? You need the acceleration. How are you going to get the acceleration? Position. First derivative is velocity. Second derivative is acceleration. Okay? We are not using acceleration of gravity because there's no mention of gravity here. Right? So for us to get our field, what we need to do here is take our second derivative of our position. And that will give us our, this is going to be our acceleration function. And acceleration times mass equals force. So this is, I was going to give you the hint of Isaac Newton. Force is mass times acceleration. We have the mass. We just need the acceleration. So we take the second derivative of this, bam, bam, that's our acceleration. We multiply it by mass, so multiply it by 10, and that will be our field. All right? Yeah, we'll call it a day. You understand what you need to do here? Yeah. Two derivatives, multiply by 10, dot that with the derivative of this, okay? Integral from 0 to 1, That's the way that would work. All right, what's due next time? That bonus is due, and then also there's a mini exam, right?
Yeah.
And I think at the end of last class I said that we had covered everything.
Yeah.
Is that right? So, yeah. All righty. Have a good one.